Being able to do so is a good indication that one has mastered the language. Recall from earlier mathematics that a theorem is a statement that can be proved to be true by reasoning. Is an argument valid? Does it make sense? Yes, only if it follows rules of inference. If based on fallacies, the argument is deemed invalid. Here are some rules of inference we can use. In each of these, the last statement, the part after the horizontal bar, is the conclusion. All its preceding statements are called premises or hypotheses. The symbol with 3 dots in it is read therefore. In this list, we have addition, simplification, conjunction, modus ponens, modus tollens, hypothetical syllogism, and disjunctive syllogism. Each of these can also be written horizontally. For example, modus ponens can be written as P and P implies Q implies Q. Let us have some examples. Anna is a human resource management major. Let us denote this as P. Therefore, Anna is either a human resource management major, which is P, or a computer applications major, which is different from P. Let us denote it as Q. Hence, the argument is valid because it follows the addition rule of inference. Next example. Ben is a game designer and also a game developer. This is a conjunction which we can write as P and Q. Therefore, Ben is a game designer. Hence, the argument is valid because it follows the simplification rule of inference. If it is rainy, then the oval will be closed. P implies Q, with P being it is rainy, and Q being the oval will be closed. It is rainy. Therefore, the oval is closed. This is valid by modus ponens. If it rains today, the college will close. P implies Q, with P being it rains today, and Q being the college will close. The college is not closed today. Therefore, it did not rain today. This is valid by modus tollens. If I go swimming, then I will stay in the sun too long. P implies Q. If I stay in the sun too long, then I will get burned. Q implies R. Therefore, if I go swimming, then I will get burned. This is valid by hypothetical syllogism. Now, beware of so-called fallacies. Some of them look like our rules of inference, but they lead to invalid arguments. Consider, for example, the fallacy of affirming the conclusion. If you write it vertically, we have P implies Q, Q, therefore P. Notice that this looks very much like modus ponens or modus tollens. Similarly, writing the fallacy of denying the hypothesis vertically, we have P implies Q, not P, therefore not Q. Lastly, begging the question or circular reasoning happens when an argument's premises assume the truth of the conclusion. Let us have some examples. If you do every problem in a math book, then you will learn mathematics. You learned mathematics. That would be Q. Therefore, you did every problem in the book. That's P. This is a fallacy of affirming the conclusion. Now, how can you fix this? If you use modus ponens, you say, if you do every problem in a math book, then you will learn mathematics. You did every problem in the math book. Therefore, you learned mathematics. If you do every problem in a math book, then you will learn mathematics. You did not do every problem in the book. Therefore, you did not learn mathematics. This is a fallacy of denying the hypothesis. Again, you can fix this using modus ponens or modus tollens. Let us end this second part by discussing some methods of proving theorems. There are several methods, but we will limit our discussion to the first four: Backus proof, trivial proof, direct proof, and indirect proof. All these four methods can be used to prove implications or if-then statements. How? For Backus proof, we only need to show that P is false. This is enough because, as you see in this truth table, the implication P implies Q is true if P is false, regardless of the truth value of Q. For trivial proof, we only need to show that Q is true. Again, this is enough because the implication P implies Q is true if Q is true, regardless of the truth value of P. For direct proof, we follow modus ponens. Step 1. Assume P. Step 2. Show that Q follows. Lastly, for indirect proof, we follow modus tollens. Step 1, assume not Q. And step 2, we show that not P follows. Let us have an example for each method. In this first example, we are being asked to show that P of 0 is true using vacuous proof. But what is P of 0? P of 0 is the implication if 0 is greater than 1, then 0 squared is greater than 0. 0 greater than 1 is P. 0 squared greater than 0 is Q. Since P, which is 0 is greater than 1, is false, the whole implication P of 0 is true by vacuous proof. And we're done. In the second example, we are being asked to show that P of 0 is true using trivial proof. But what is P of 0 here? P of 0 is the implication if A and B are positive integers with A greater than or equal to B, then A to the 0 is greater than or equal to B to the 0. A and B are positive integers with A greater than or equal to B is P, while A to the 0 greater than or equal to B to the 0 is Q. Now, since any positive integer raised to the 0 is 1, A to the 0 greater than or equal to B to the 0 is equivalent to 1 greater than or equal to 1, which is true. Hence, the whole implication P of 0 is true by trivial proof. And we're also done. In the third example, we are being asked to give a direct proof of the statement, if n is odd, then n squared is odd. N is odd is P, and n squared is odd is Q. Step 1. Assume that n is odd. We can then write n equals 2k plus 1 for some integer k. All odd numbers look like this. For example, 5 can be written as 2 times 2 plus 1. Step 2. We show that n squared is also odd. N squared is 2k plus 1 squared, which is 4k squared plus 4k plus 1, which is also 2 times quantity, 2k squared plus 2k plus 1. This shows that n squared is odd because it is 2 times something plus 1. Therefore, the theorem is proved using direct proof. For our fourth and last example, we are being asked to give an indirect proof of the statement: if 3n plus 2 is odd, then n is odd. 3n plus 2 is odd is P. N is odd is Q. Step 1. Assume that n is even. This is the negation of Q. We can then write n equals 2k or some integer k. All even numbers look like this. For example, 4 equals 2 times 2. Step 2. We show that 3n plus 2 is even. This is the negation of P. 3n plus 2 is 3 times 2k plus 2, which is 6k plus 2, or 2 times quantity 3k plus 1. This shows that 3n plus 2 is even because it is 2 times some number. Therefore, the theorem is proved using indirect proof. We end the demonstrations here, although there are other methods of proof discussed in the book. Those are left to you for your further investigations.